Jesus. All right, welcome back to the stream, everyone. We're doing another biophysics stream today, and I am Chemistry Star, your host. Um, we're going to just jump right into it. Let me pull up some tabs here. All right, 1 second. Okay, we're going to go with some bookmarks. Just give me 1 second. I'll pull it up right now. And I should probably put some like clear cast. There we go. Much better. Cool. All right, 1 second. Let me pull up all the bookmarks that I saved, and it's gonna be bookmarks. Yeah. Oh, got it. Okay, I got all of our bookmarks loaded up, and why not put some music on? I'll just put like something very mellow. All right, that's mellow. Hopefully that works. I feel like it's not loud enough. That's good. Something in the background, you know. All right, so we are. Where are we? We're preparing our PDB file. Let's zoom in so you guys can read it. So, where are we? All right, we did this step. So, in our last stream, I noticed that we wanted to find a lot of sulfuric acid hydrates inside of the atmosphere of Venus. So, what do we do to get that, right? Like, how do we find the size of a sulfuric acid hydrate? Well, the thing is, since it's a hydrate, it pretty much clumps onto each other. We can find the atomic size, but then we should be able to guesstimate whether a bunch of them clumped together could form a size that was that was reported to be like 180, like 180 nanometers in diameter, and that's kind of nuts. Let me pause that. So scientists have determined that there are about 150 to like 200 nanometer particles inside of the atmosphere of Venus, which means, I mean, it could be anything. My guess is that it's not life. However, it could be. So, what we're going to do is save a bunch of money. We're not going to fly over to Venus and pick up a sample, right? Because that would be expensive. We're going to use physics to simulate the atomic interactions in a controlled space where we get to say we're the boss. We can control all the things inside of our simulation. We can make it look a certain way. We can make it um, hexagonal. We can make it heptagonal. We can make it square. We can make the simulated space any shape we want. Circles kind of like, unless you have a really good computer, having a sphere is kind of tough. But we can do like squares. You know what I mean? Um, that just brings us to like a calculus type of idea where the more, it's kind of like a histogram where the more data gives us the more jumps, and then we'll be able to see, wow, okay, this is our sample size, and histograms work better with a lot of data, and that gives them a an edge. That's why people use histograms. It kind of shows you where your volume is at a certain range. And so when it comes to simulating things, we're gonna do a square. I'm sorry, a cube. We're gonna do a cube. So we'll have a cube simulated with something inside of it, and it'll do exactly what we say it will do, like according to the laws of physics. So we'll just carry on from the last video where we were looking for the next step. We were preparing our PDB file, which we downloaded online, and now we're going to be using open source software that we installed in the previous two videos. Um, it will teach you how to install it. What I learned the hard way is make sure you install in your root directory. That will save you. So you're going to use two commands, um, sudo su, and then the second command is scp to move your files that you download to that root directory, or um, you can learn on your own. But that was the easiest thing. Like it took me hours to figure that out. I was like, okay, install in the root directory, and then number two, you're going to update Linux on your PC. So just make sure you install Linux and install your open source platforms within the root of Linux. So sudo space su. That's the commands that I learned. That'll save you a lot of time. And now we're here at maybe like we're on 3.2. So we did chapter 1. Chapter 1 we finished, which kind of helped us prepare files. I had to let my computer run for a while because it was doing physics equations and stuff, just like a bunch of math, a lot of matrices. And eventually it finished, and now I have a prepared file. So the file looks like this. I just ran a free program. It's called VMD. It takes a little bit of time to run because my computer has a lot of things running right now, so it probably would just take a little longer. So I put everything in the test file. Okay, so this is the standard file that you download on the internet. It's a protein database file. And look, it's simple. It's got a protein. You what this protein where this protein comes from is actually from the staph infection bacteria. So they scientists in the laboratory isolated enough of the staph bacteria in a petri dish where they were able to put it within a specific solution and then add it to a cryo-electron microscopy instrument. And so cryo-electron microscopy is a very expensive way to say we can see the atomic structures like this and kind of take a very, very good mathematical approach to guessing what atomic structures look like here. And you kind of see proteins are kind of just building upon themselves. And that's what it is. You know, there's always a beginning and an ending to a protein strand. And we're just made of like a lot of them, you know? So in biology, they talk about a C and an N terminus up the protein chain. So N terminus, that's the beginning where the protein is, well, the amino acids are being assembled in a specific orientation, kind of like here. Like, let me show you. Let me do something about this so you can see it better. Graphics. Oops, I jumped the gun. And now oh, maybe we'll do this one instead. Bonds. That works. All right. So you can kind of see that the chains of proteins are in a very specific way connected in series. There are different types of amino acids, obviously. Some of them have nitrogens on certain areas. Maybe they have uh, an iso group, which is like a carbon with two carbons attached to it. They have methyl groups, hydroxides, and the reason why everything is different is because of a few reasons. First off, the way that electrons like to orbit atoms aids in its electronegativity, right? So some amino acids like to have a little bit of a charge to it, and some acids don't. Uh, and there are tons of examples where they say the charged molecules in a system allow for the natural movement of carrying charge carrying atoms, and also, for example, like if everything was just stable, well, nothing would do anything. It would just be everything would be happy and nothing would have to exert energy. However, since we're in an imperfect atmosphere and world, it gives us the drive atomically to keep moving. So that's the beauty in it. It's kind of like what's a good example? Kind of like the Big Bang, you know? It's like all of a sudden massive pressure and heat just like, you know? But here's another example. It's kind of like there's a pendulum, right? And it's not moving in proportion with many other things. The pendulum is just standing still. But if you move it with gravity, with friction, right, it would stop eventually. It might not immediately, but because of its counterbalance, it'll keep going for a while. Well, let's just say that you move that pendulum and it didn't stop. Well, that can be all controlled by a simulation. The thing is, we want to be as realistic as possible. So we want to make sure we include as many realistic uh, circumstances, such as pressure, temperature, and integrate them within the environment, because we actually do have the ability to. Like, they give us a little like space and like, oh, put what temperature do you want to run the system. Well, it's because some amazing engineers out there spent the time and developed the software based off of well, just plain old math. You know, math and software engineering is a beautiful thing. Like, they came together like, oh yeah, we're gonna make this. This is gonna be something fun. And I'm sure they had some hard times, but the end result is having a simulation done within your computer. We can make a lot of calculated discoveries that way. And the best thing is, you don't have to have a laboratory if it's just simulated in your computer. Like, you can literally have a simulated lab in your computer and just do things, figure out things, and you don't have to spend a dime except for maybe electricity. And you know, you have to obviously do something about the overhead, but for free, you know. So there's this, and then, well, where are we? We did this. Okay, so this is the VMD protein that we started off with, and now I'm going to show you what we got to. So let me delete this and add a new file, which is the most up to date protein file that we generated with some specific conditions, such as we want to have a lipid layer, which is like the membrane between organelles within a cell. Organelles, kind of like you know what I mean. Like, organelles contain different parts of inside of the cell, so it's kind of like this. It's kind of like the skin of the organs, and it's made out of protein, bilipid membrane, and there's a negative charge, and then there's a positive charge, and that's kind of what keeps the membrane looking the way it does. It's great. It's the charges, the electrons really gives us the possibilities to do everything. Electrons power our computers. They're just the greatest thing. You know, if I can choose one thing about this life that I love is electrons 100%. Okay. So, here is the new one we updated and checks out. Oh, did it not work? Let me try one more thing. Okay, let's figure this out. There you go. It's gonna take some time. It's a little slow. I'm gonna put some music on while we wait. Oh, it's up. All right, that was quick. So now that we have this here, let me show you what we did. Yeah, graphics. Let's change this by selecting a chain that represents what we want to see. Let's do chain A. Whoa, look at that. We created the bilipid membrane right here on the bottom and our bacterial strain right here on top. So now that we have staph bacteria here, we're gonna throw this sucker on Venus and see if it survives. Yep, we're gonna do that. It's gonna be good. So the next step after creating this simulation of just a single frame of our bacterial staph aureus, or was it staphylococcus, staphylococcal something, staphylococcal aureus? That's the one. Yeah, it looks really pretty, although it messes us up. Like it's horrible for us, but it looks cool. It looks like a little tree. It's good to have an RTX graphics card can do stuff like this. Anyways, yeah, you can kind of see like that is the side of so a lot of electrons on, I'm sorry, there's a lot of hydrogens on this side, most likely whichever side the protein. You can see by the red, there's a lot of red here. That's a lot of hydrogen. I'm sorry, I mean oxygen. My mistake. That's oxygen for sure. All right, oxygen, and then yep. So it looks like whichever side staph exists on is a very oxygen-rich environment. Just, just like tons and tons of oxygen. It's kind of surprising because it most likely requires oxygen. So I'm sure if someone inhibits the oxygen of a bacteria like this, then most likely can wipe out. I mean, sure, oxygen is vital for all, like all micro systems. So it's kind of a tough one. You can't just like get rid of the oxygen. You just kill everything. It's horrible. Biology is so grim sometimes. Um, but it is pretty. Look at that. I love playing with proteins. It's fun. And also, some marvelous things can occur from it. Wow. That's so cool. Alright. Some music on. We'll just like listen to some Super Mario music and just look at this thing. Hey, what's up? Hello? Can you guys hear me? All right. So we're just looking at this protein that we developed on top of a biolipid membrane. In biology, that means that we've developed the separate the separable barrier between the organelles and the cell on top of putting our specific bacterial protein file within that system. So we've developed a specific box that contains exactly how many liquid molecules in there. We know exactly how much of that's there. We know exactly how much protein we've got working with because we had to do that custom. Um, we had to specifically download this bacteria. Then we had to clean it up and take out all of the extra stuff and then put in our extra stuff, knowing how much we put in. And now we have a more controlled system. So the next thing we're going to do is take this bacteria within a kind of like a simulated cell type of circumstance, and then we're going to get rid of everything but the bacteria, and we're going to run a gas phase amber 9 simulation. And what that means is we're going to simulate using Amber, which is the open source tool we downloaded, and the version of the simulation is 9, which means that it's a gas phase. We're going to turn this protein into a gas phase, kind of like a vaporized version of the protein. And that will be more realistic because, well, first off, in the atmosphere of Venus, we've got tons of different phases. We have saturated sulfuric acid. We have the hydrated form of sulfuric acid as well. So we have a vaporized, superheated sulfuric acid. We have a very cool, like a super cooled sulfuric acid, and we have a solid phase sulfuric acid, which is the hydrate form that's existing in there. So within the super cooled section, so the superheated, that I'm only guessing is when the sun is directly contacting the outer layer of Venus. That would be where the superheated sulfuric acid would be. But on the inside, I'm my guess is that as hot as the surface gets, there's still super cooled sulfuric acid hydrates within deep enough of Venus. So it's interesting to think, or I could be wrong, and as soon as the sun hits the surface, that whole side is like just flame on. But since it's that much closer I can only assume that the temperature of the surface when the sun is directly in contact with Venus could be ridiculously hot, you know? Um, well, that's why I'm considering there's multiple phases, like physical phases of the sulfuric acid that's on Venus. So that's why we're going to do gas phase first, and then after that, we're going to run liquid, and we're going to change temperatures and pressures because the paper we were reading told us that from the surface to the top of the atmosphere, there's a specific atmospheric pressure there. And we're not going to take guesses here. If someone's published that on NASA's website, we're going to go with it. Like, we'll run with what they've sent because I'm sure other people have tried to duplicate the data. And if they redacted it, it would have been done by now. So we know that their numbers are at least somewhat close. You know, it's not like exact, but it's going to be very close to what we want. So we're going to do a gas phase first, a gas phase simulation using Amber 9. Then we're going to run a liquid phase uh, simulation using, I'm not sure which version of Amber we're going to be using. However, the the liquid phase will be a much colder temperature. So we know that we'll have to set the simulation at a specific temperature, most likely, like, God knows, it'll probably be very cold. I don't know the number off the top of my head. And then the next thing we're going to do is we're going to run a solid simulation of the of this protein within well, what I mean by the phase changes is that we're going to expose our proteins to as much atmosphere of Venus as we can within our computer. So if Venus has a bunch of sulfuric acid, we're going to throw that all in the simulation. And we're going to first change the temperatures, the type of molecules that the solvent will be. Because Amber doesn't have the solvent that we're looking for, we're probably going to have to custom make a solvent using the available tools at our hands. And the solvent we're going to be making are all of the different types from the beginning to the end of what Venus's atmosphere contains. So when we hold on. So yeah, we're going to create solvents for Amber. I'm sure that if they don't exist, we'll be the first ones to make them and provide that as an open source like contribution to the community. And also that would be just for biophysics too, because people love when people contribute stuff. And even if it's not 100% right, someone will figure out like, oh, what's this problem? Like they'll look into it and try to fix it. So biophys is really fun, and it's a great thing to do. It's fun to do. It's free, and if you're bored, if you want to like figure out how you can custom make protein files, or if you want to learn more about biology and chemistry or physics, this is kind of something you should be playing with, because not only is it fun, but what if you discover something amazing? Like I discovered something pretty freaking cool, and well, to be determined. Hold on one second. Okay, so what? Okay, so where were we? We were looking at adding acetyl groups to the beginning. All right. Well, we pretty much went over that proteins have a lot of errors in them when you're customizing them for your simulations. And you'd have to sometimes, instead of letting the program autofill all the gaps, which kind of makes it difficult to be very genuine, because when you auto add endings to a protein chain, you change the chemistry of it. So you have to be very careful and only choose ones that make sense. Like, for example, instead of replacing a gap that is missing part of the protein chain because of some sort of glitch, um, you don't want to just put anything. You want to see where you are. So if there's like histidine and like a lysine next to each other, then you know that, for example, the amino acid that's positively charged next to another positively charged is most likely going to be negatively charged. So, what kind of amino acids are negatively charged? You're going to probably want to choose one that is, first off, not too large, that it kind of blocks other amino acid. You want to choose the right size, pretty much the right size in electronegativity, in its polarity. You want to get something either polar, non-polar, and there's a lot of things that are polar. So you want to make sure you choose the right one. And the only way you'll find out is if you just sit down and ask AI, like, "Hey, there's these kind of proteins next to each other. What are the odds that the next one will be non-polar?" You know, just ask. Uh, Copilot. Copilot's a good one. I do not do ChatGPT unless you want to just. What is 2 plus 2? 5? No, like that. Dude, ChatGPT is intentionally messing with people, and it's hilarious. Like I'm just sitting down eating my popcorn, watching. I'm like, wow, people are gullible. Like, psh. But ChatGPT can be good in some occasions. Most occasions, I like Copilot more. Copilot's so much better. So let's keep going. We finished this. Did that. I think I did this one. Let me double check. Yep, I did this. I did that. I did this. Yes, I did that. All right. So where we at? Where we at? Lipid extension. All right. All this is just different types. These are different types of lipids that you can add to your chains. All right. So what we're gonna do is this. We want to leap in file. Cool. Let's open up our Linux and get started. All right. So let's see. I'm gonna set my directory. Oh wait, let's see. Users. Oh, desktop. All right. Let's see. Okay. All right. So what we're gonna do is we're going to do this. Okay. We're gonna try this. Oh, right. All right, I ran into an error. Let's see. All right, so let's see what we got. All right, if you're joining us, we're just learning a little bit about this program. It's an open source program. We downloaded it, installed it on Linux. All right, this is better. All right, cool. So we just downloaded Amber, and we're learning how to use it now. So we've got let's see what we got here. Okay. I think we're good on that. We're going to go ahead and jump onto Solvate. So we'll just go ahead and do this then. Okay. So we're going to do oh, I see. We're going to need two files. Let's see. So what I just did, I have to download a PDB file for sulfuric acid, and let's find it. rcsb.org. We're going to download a PDB file for H2SO4. You know what? We're just going to do. Oh. Okay. Cryo-EM database, EMDB. Is that it? Yes. Okay. H2SO4, that is sulfuric acid. So I just type it. H2SO4 PDB file. Maybe we can find a PDB file here. I don't know. We're gonna find it. Download, yes. Hmm. Interesting. Can I upload JSON files? Let's see. All right, SDF. XML. Nope. I found something. No, no, it's just an entire structure. Did I skip it really? No way. There it is. SO4. Great. Just add a hydrogen and you got H2S. That's just great. Okay, cool. We'll just put a bunch of these. Let me see if I can upload those. SDF, huh? Let's see. SDF. Hmm. All right. Copy this. Notepad it. So I got my notepad open. Now I'm gonna paste this and save as H2SO4 and put it on the same directory that I was working on. And I'll put it as all files and .pdb. Done. Now let's see if this freaking thing works. Cool. Now we're doing 8 times 0, 1 to e to the negative 6. So it's pretty high. It's a high concentration. It's the highest concentration I saw at the top. I'm sorry, was it at the bottom? If it was high concentration. Well, I'll just take a look at the article right now. Hold on. There we go. 8.1 times 10 to the third from bottom to top of the cloud. So the top of the clouds is the highest concentration of sulfuric acid. So 10 to the 3. So 8.1 times 10 to the 3. What I put? 8.01. All's close. by like 3 magnitudes. So let's see. Let's see if this works. All right, we'll just do this then. Cool. So now we've used our solute PDB of H2SO4.PDB, which is just pretty much SO4.PDB. The H2 does not, there's no hydrogen in that PDB file. So the solute to be added is going to be of a concentration of 8.1 times 10 to the third molarity. So we'll just wait for this thing to run and we'll see what happens. Solute to be added. Oh my god, this is going to be so fun. If this actually works, how fun and how cool would that be? Holy cow. That's insane. So, yeah, we'll see what my processor's usage is. Probably 100. Was that right? Look at that. Look at that. 100. Look at that. Reduce is working. All right, it's pretty much replacing thousands of parts of like hundreds of thousands of parts of my protein file and putting a solute into the mix. It's adding it. It's pretty much adding what I want to add to the solvent. So we know that the solvent's going to be like a mixture of the atmosphere, but the solute is the protein and also tons of sulfuric acid. So we're going to throw in a bunch of solute first, and then we're going to throw in a bunch of hydrogen. We're going to have to throw a bunch of hydrogen in. So most likely there will be tons of hydrogens thrown into this after we finish the sulfuric acid. Then after that, we're going to make a movie and see if this thing survives. You know, this kind of stuff like gets me thinking. If I had like a very strong computer, like maybe like a Threadripper, like 64 core processor with tons of like GPU processing power, like using CUDA, then this thing would just finish so much faster. All right, I'm gonna go get a drink while this thing's running. Maybe just be right back. Yeah, it's fine. I'm still chatting. Gaming? Nope. Sorry, I'm really new to this. Oh well, just turn that off. All right, well, let's take a look. What we got? Maybe we did some of it. I don't know. We'll find out. All right, let's take a look. We got some sulfur in here. Let's make them large. Okay. Now let's turn on. Chain where the. All right, chain is right here. Now you're seeing a couple of these sulfur um, ions being added outside of the protein, right? That's exactly what we're doing right now. They're just hovering in the air. That's what we want. So we're doing it right. Like, no matter how early we are into processing this, we got at least 20 of these things just floating out here. That's exactly what we want. That's so sick. That is so cool. Staph infection. Wow. So yeah, now we're gonna wait for this thing to finish, and we'll see where we are. But you can kind of see like we've got some sulfur processing, and we're on our way. Like this is good. This is real good. Oh, okay. We ran into an error. That's fine. So let's delete this. One, almost 2 million atoms in this thing. It's crazy. Check, check. Yo. All right, there we go. Hmm. All right. So we ran into an issue. It pretty much said that that PDB file that we made was invalid. I had a feeling it would happen. So what we're gonna do is we're gonna search for one. Oh, cool. We got it. We got the PDB file for sulfuric acid right here. Look at that. Now this should work. So all we gotta do is get into our file and do this. Watch. Cat H2SO4.pdb. That's it, right? Okay. We're just going to do this. We're going to do um let's see. How do I do it? Darn. Hold on one second. It's what's it called? It's oh yeah, right. Okay, that's it. I figured it out. So all you gotta do is nano, then H2SO4.pdb. Cool. So that's it. Now we got to delete everything. Cool. How do you delete everything? Like that. Delete. Wait, it won't let me do that? All right. How do you... Wow. Oh, it doesn't let me mass delete. I'm going to just have to hold this for a second. You know, it would probably be easier if I just did this. Control um, Control X. No. And then oh, what oh, oh yeah, rm remove directory h2so4.pdb. How you do it? Remove, what was it? Like it's removing file with Linux. RM. Cool. So it's just RM. Okay. So RM h2so4.pdb. Okay. We deleted it. Now make h2so4.pdb. How do you, making file in Linux? It's oh cool. So you just have to do cat. Okay. So all you gotta do is do this cat h2so4.pdb. Oh, what was it? Oh, cool. That's it. You okay? The funny thing is, the command to make a new text file is that. So just do touch and then text file in Linux. That's hilarious. Just touch it and it'll turn on, or it'll be created. Okay, so now I'm gonna nano to so4.pdb, paste the information for our h2so4, and then save it, which is yes, we want to save it. Done. And then cat h2so4.pdb. Yep, we did it. Look at that. Now let's go ahead and run our simulation again. This should work. No ratio, huh? Okay, so I'll be back when this is finished. Oh, always the problems. All right, it didn't work. Well, interesting. Huh. Okay. So, all right. So that didn't work. Atoms. It doesn't say anything about atoms. Maybe I should convert H2SO4 into an actual like amber file. So PDB for amber H2 PDB H2SO4.pdb. Oh Jesus. That's scared the crap out of me. Whoa. Alan James, welcome to the room. Right now we are trying to determine what the error is. We're trying to add sulfuric acid to a bacterial staph staphylococcal aureus. It's a staph infection, and we're just trying to throw in as much sulfur as possible, which is technically what Venus has in its atmosphere. So that way, when we use a physics simulator to create a movie for us, we'll see whether or not staph infection or the staph bacteria is what NASA saw in the atmosphere at around like 150 to 180 nanometers in diameter. So eventually, we'll determine if this bacteria can survive at all just by using physics. And yeah, it saves a lot of money. We don't have to fly over to Venus and take a sample. So the computer is great. Like, let the computer travel for us is what I like. It's way easier, and plus my computer sucks and it still does it, so it's not that bad. I'm planning on getting a new computer soon. That'd be actually so cool. Like, I've been working with this computer for years now, and it's a champion. Dang, like MSI, I was just like, I was a little shook, and I was like, wow, are you really gonna work this well for this long? I mean, it does great. As an RTX 2060, you're like, 2060, you know. Anyways, but yeah, I was thinking about the 4090 one day. Anyways, thanks for the follow, Alan. Okay, so yeah, well, it's giving me errors here. So you know what? I was thinking maybe we can just ask Copilot to fix it for us. Cool. Here it is. So what I'm going to do is I'm going to copy and paste my PDB file and be like, this is my protein database file information for sulfuric acid. I want you to fix the error I get got from trying to integrate this solute within amber molecular dynamics. This is the error I received. So I'm going to just copy and paste the error, and hopefully it will teach me what I'm doing wrong here. But, right, it's right here. Okay, so It looks like it kind of seems like all right, we're gonna open up, we're gonna listen to what Copilot's got to say, and this is what it's telling me. I don't see that number. Okay. So it's saying here that yeah, it's definitely a little difficult because it's telling me that like find the line that says 186A1 but doesn't exist. I looked inside the file. This is like playing Fallout, I swear. You're trying to hack the terminal, but it's all fun. All right, let's see. Let's do this. Oops, I put ration. Ration. Let's see. Okay, the ratios are messed up. I gotta figure that out. All right, so ratio. Let's check it out. We've asked Copilot AI to help us out, and we hit a brick wall. So what we're gonna do now is um, we're going to figure out how to get a like. Oh wait, we got a message. Let me hold on 1 second. Hold on 1 second. 1 second. All right, so just sending message. Hold on. Okay, so practically right now we're going to be trying to figure out how to get a working solvent model for our protein. So this is it's telling me a couple of errors. Maybe if I ask Copilot to like fix, can you fix my PDB file to work? Just ask it to do it. All right, check this out. Okay, let's see if this works. I don't think it did anything. Let me just check on. Sometimes it just doesn't do anything. Here, I'll just paste it. Honestly, nothing changed. Nothing changed. It's like I did it. I did nothing. Copilot, oh my gosh. AI is so silly nowadays. Alright, we'll go back to the structure file. So I mean we got the PDB file from here, but I mean like I don't know. I don't know. I tried to download it and it just didn't work. See, I don't. That looks like a protein file. Perhaps I have to put like a TR somewhere. Let's do. Here, I'll try this. I'll put a terminate the line right there. And let's see if this works. All right, so yeah, it just gave me the same error again. PDB volume, PDB atoms. Wow. So that's not working. Okay, so it didn't work. So let's just keep looking for more protein files. We're trying to find a protein file that represents this. See, I found it here, but it just doesn't work, which is so silly. Let's see. I think I'm blowing, breathing into the mic. There we go. Oh, whoops. Okay, so cool. We found Purdue's Department of Chemistry, and no, this is just just like JavaScript. Okay, so if you're new to the stream, we're just trying to figure out. Maybe they have a protein file we can download. Who knows? We're gonna find. Oh, didn't work. Maybe we can find. Yeah, I don't know. Okay, how to download sulfuric acid PDB. Just Google it. Okay, cool. There we go. Hi, bye Rosetta. It's awesome. I don't have Py Rosetta. All right, let's take a look. See what we find. Okay, let's do this one instead. Oh, that's cool. Let's see. Okay, so it's got everything in an FTP file just available to download. That's awesome. This is exactly what I wanted. Bio unit assemblies. What's that? Wow. It's like every protein file ever. It's like a direct access to like all these files. It's crazy. Wow. It's so cool. All right, we got some work to do. Let's figure this out. I'm gonna query this site. But damn, a long day. I'll be right back, guys. What a dick. Flip that fool.